Welcome to the Explainer. So let's just dive right into this, shall we? Today, we are embarking on a high-tech digital mapping mission, descending way, way below the surface to explore the completely hidden topography of the world's oceans. You know, for the longest time, the bottom of the ocean was this massive mystery, totally invisible to us. But today, thanks to some seriously advanced data and mapping techniques, we can actually visualize this massive, almost alien landscape that covers over 70% of our entire planet. So strap in because we're going on a transect from the shallow sunlit shores all the way down to the deepest, absolutely most extreme environments on Earth. Topographical scan initialization. Think of this as your mission briefing. We're going to target 4 distinct geological zones today. First up, mapping the ocean floor. Number 2, exploring continental margins. Third, deep ocean basin features. And finally, number 4, mid-ocean ridge structures. All right, Section 1. Mapping the ocean floor. Let's initiate the very first phase of our scan. So how do we actually pull off a modern digital scan of the ocean floor? I mean, you'd probably think we just use sonar, right? Well, yes, ships do use echo sounders, but think about it. Sending ships back and forth across the entire global ocean, that would take way too much time and resources. So we look up. We look to space. Satellites orbiting the Earth map the seafloor not by trying to see through the water, but by actually measuring the water's surface. It's wild. Massive underwater mountains and trenches exert these gravitational pulls that literally create permanent abnormalities, like tiny little hills and valleys on the sea surface itself. Satellites use radar altimeters to measure those surface variations, and from that data, we can mathematically calculate the shape of the seafloor down below. And comparing these two methods side by side reveals exactly why this is a total game changer. On the left, you're looking at bathymetry, which is just the study of underwater depth, derived purely from ship data. Notice how it's full of gaps and kind of blurry patches? Now look on the right. That is the exact same area, but mapped using satellite remote sensing. The level of detail is just staggering. We can suddenly see distinct ridges, valleys, and textures that were completely invisible before. This high-resolution satellite data really sets the high-tech standard for the rest of our journey today. Moving right along to Section 2, exploring continental margins. With our mapping tech fully calibrated, it's time to leave the coastline behind and start our descent down the submerged edges of the continents. The really crucial point to grasp here is that not all coastlines are created equal, geologically speaking. We basically draw a hard line between 2 types of margins, passive and active. Passive margins are found where tectonic plates are moving apart. They're pretty quiet, featuring these broad, wide shelves with very little seismic or volcanic activity. It's just a smooth transition from continental crust to oceanic crust on the very same plate. Active margins, on the other hand, are a totally different beast. These are found at converging plate boundaries, where the oceanic crust is actively subducting or diving right beneath the continent. Because of that violent collision, active margins are narrow, they're steep, and they are plagued by huge earthquakes and explosive volcanoes. Let's anchor this with a real-world geographical example. Take a look at this cross-section of South America. On the left, the west coast is a classic active margin. You have the oceanic Nazca Plate literally crashing into and subducting beneath the South American plate. That action carves out the massive Peru-Chile Trench and actually pushes up the entire Andes mountain range. And notice how incredibly narrow the continental shelf is right there? But if you look over to the right, the east coast facing the Atlantic, that's a passive margin. The shelf is broad, it's wide, and it gently transitions into the deep basin with absolutely zero violent plate collisions going on. Now, as we continue our descent down a typical margin, it generally happens in 4 distinct steps. Step 1 is the continental shelf. This is a nearly flat, shallow area that averages only about 130 meters deep. And here's a crazy fact. These were actually exposed as dry land during the last ice ages. Step 2 is the shelf break, which is exactly what it sounds like. The sudden, abrupt edge where that flat shelf just ends. Step 3 sends us plummeting down the continental slope, which is this really steep descent down into the dark. And finally, step 4 is the continental rise, a much gentler slope at the very bottom created by massive piles of sediment that have basically just cascaded down from the continent above over millions of years. So, you might be wondering, how does all that sediment actually make it all the way down to the continental rise? Well, it happens through something called turbidity currents. You can think of these as absolutely devastating underwater avalanches. Triggered by things like earthquakes or just an overloading of sediment up on the shelf, these dense, heavy clouds of mud, sand, and water come roaring down the continental slope, reaching terrifying speeds of up to 90 kilometers per hour. And these 90-kilometer-per-hour currents, they don't just flow over the surface. They physically erode the Earth. Over thousands of years, these incredibly violent flows carve out massive V-shaped submarine canyons right into the edge of the continental shelf and slope. All that sediment is then spat out at the bottom, kind of fanning out onto the deep-sea floor. It is just an incredibly dynamic and really destructive process, and it's happening right off our coasts. Okay, Section 3, Deep Ocean Basin Features. Having survived the steep drop of the continental slope, we transition to the vast, incredibly deep expanses that actually cover the vast majority of the ocean floor. Down here, the landscape is completely defined by extremes. If you scan this composite view for thousands of miles, you'll find abyssal plains. These are, hands down, some of the flattest, most featureless places on planet Earth. Why? Because for millions of years, fine sediment has drifted down from above, sort of like snow, perfectly masking the rugged basaltic crust beneath it. But this huge flat expanse is violently interrupted by abyssal hills, towering volcanic seamounts, and massive, plunging deep-sea trenches. Now, among those underwater mountains is this really fascinating geological quirk known as a guyotte. A guyotte is a submerged volcanic seamount, but it has a perfectly flat top. So how on earth does an underwater volcano get a flat top? Well, at one point in its history, this volcano grew so tall it actually breached the surface of the ocean and became an island. Then, over time, relentless surface wave erosion literally sawed the top of the volcano completely off. As the oceanic crust cooled and sank over millions of years, that flattened mountain was dragged back down into the cold abyss, perfectly preserving its flat top deep underwater. Nature is amazing, right? But volcanoes aren't even the most extreme feature down here. That title definitely belongs to the trenches. 11,020 meters. That is the staggering depth of the Challenger Deep, located inside the Mariana Trench off the coast of Japan. To put that massive number into perspective for you, if you were to drop Mount Everest straight into the Challenger Deep, its peak would still be completely submerged under more than 2 kilometers of water. It's just an awe-inspiring scale of depth that really represents the true limits of our planet's crust. So the really crucial takeaway here is understanding exactly where these massive trenches form. Like we learned earlier with active margins, trenches occur at convergent plate boundaries, right where one plate is being destroyed by diving under another. If you look at this global map, you'll immediately see this bright red perimeter lining almost the entire Pacific Ocean. The Pacific is completely bordered by these subduction trenches. As the diving oceanic plates melt down in the Earth's hot mantle, magma rises back up, powering a nearly continuous chain of explosive volcanoes and massive earthquakes. And that is exactly why it's earned its famous title, the Pacific Ring of Fire. All right, Section 4, Mid-Ocean Ridge Structures. For the final phase of this explainer, we're going to ascend from those deepest trenches to explore the massive underwater mountain ranges that literally divide our oceans. I want you to let this number sink in for just a second. 75,000 kilometers. That is the total length of the mid-ocean ridges. It makes it by far the longest continuous mountain chain on Earth. It literally wraps around the entire globe like the seams on a giant baseball, completely dwarfing absolutely any mountain range we have up here on land. Let's scan directly across the ridge itself. This stunning false-color bathymetric view shows the Mid-Atlantic Ridge, which is separating the Americas from Europe and Africa. The defining feature here is clearly visible running right down the middle, a central rift valley. This deep valley runs exactly along the axis where two massive tectonic plates are literally being pulled apart. This ridge is quite literally the birthplace of brand new oceanic crust. And down inside that central rift valley, the intense volcanic heat powers one of the most incredible phenomena on the planet, hydrothermal vents. Here's how they work. Cold, deep ocean seawater seeps down into the highly fractured crust. It then gets superheated by shallow magma chambers lurking below, dissolves heavy minerals and metals from the surrounding rock, and then shoots back out of the seafloor like an underwater geyser. In person, this extreme environment looks incredibly alien. This specific type of vent is called a black smoker. The water blasting out of these mineral chimneys can reach searing temperatures of over 350 degrees Celsius. But here's the crazy part. Because the water pressure down there is so immense, the water doesn't even boil. Instead, it spews out these energy-rich inorganic compounds like hydrogen sulfides. In total, pitch-black darkness, completely cut off from the sun's energy, these toxic, superheated chemicals actually support thriving, alien-like biological communities. We're talking tube worms and specialized bacteria that literally use the chemicals, not sunlight, for energy. It's mind-blowing. But remember, the 75,000-kilometer mountain chain isn't just one smooth, unbroken line. Because the Earth is a sphere, the spreading plates actually tear in chunks. The axis of the mid-ocean ridge is sliced horizontally by what we call fracture zones. The active regions between these broken ridge segments are called transform faults. Right here, the tectonic plates are aggressively grinding and sliding past each other in opposite directions, which triggers massive and frequent earthquakes all along the deep-sea floor. So we finally completed our transect. We've used satellite altimetry to map the seafloor, we've plunged down the steep continental margins, crossed the vast abyssal plains, bottomed out in the freezing Mariana Trench, and scaled the volcanic mid-ocean ridges. But you know what? This incredible hard rock topography is only half the story. That entire alien landscape we just explored is blanketed by thick layers of marine sediments. Everything from dust blown off the continents to the microscopic shells of ancient plankton and even tiny meteorites from outer space. So the big question we have to ask next is, what ancient secrets do these sediments hold about Earth's biological and cosmic history? It's a truly fascinating mystery, and one that proves the ocean floor is way more than just deep water and dark rock. Thanks so much for joining me on this explainer, and keep your curiosity diving deep.